A used hoodie hits the intake conveyor looking like garbage, but the recycling line sees it as a mapped mixture of cotton cellulose, polyester PET, elastane dyes, finishes, and metal hardware that must be separated with industrial precision before a single new thread can be spun. Brand-led programs like the ones Ralph Lauren promotes only work at scale when the back end is engineered like a materials refinery. Because clothing is one of the hardest consumer waste streams to standardize, the process starts with collection logistics. Because the best recycling machine is useless if incoming feedstock is unpredictable. Take-back bins, mail-in bags, and resale returns are consolidated into bales. And each bale is tracked by source region and date so the plant can correlate contamination patterns and adjust sorting rules. Moisture and odor matter immediately, because wet textiles grow microbes and create sticky residues that foul optical sensors and clog shredders. So many facilities pre-dry or ventilate loads before they ever enter the sorting hall. The first technical bottleneck is identification. A shirt's label might say 100% cotton, but blends, coatings, and hidden elastics often disagree. And misclassification ruins fiber quality downstream. That's why high-throughput plants use near-infrared spectroscopy scanners over fast belts to read material signatures in milliseconds. Neura doesn't see color the way a camera does. It reads how molecules absorb light, which makes it effective for distinguishing cotton from polyester
nylon wool
and acrylic even when garments are dyed black. Where Nair struggles heavy prints, wet fabric, multilayer composites, the line adds hyperspectral imaging, which gathers far more wavelength data. Then uses machine learning models trained on thousands of known samples. Once each garment is classified, robotics takes over for physical separation. Pick arms with vacuum grippers or soft fingers lift items at speed and drop them into chutes by material family: cotton-rich, polyester-rich, nylon, wool, and mixed. The key reason robotics matters is that manual sorting can't keep up with millions of items. And a single % of missorted elastane can create yarn defects and breakage during spinning. Sorting is also where color gets engineered because recycling becomes cheaper when you don't have to re-dye. Dark garments are pooled into dark feedstock, whites into white, and midtones into blends, reducing dye and bleaching demand later, before fiber recovery. Garments have to be detrimmed because zippers, snaps, buttons, shoulder pads, and seam tapes are foreign objects that destroy cutting blades and contaminate fiber. Some plants use dedicated depopulation stations, where trained operators remove metal hardware quickly. But the high-tech approach is hybrid. Metal detectors flag items with large hardware, and those items route to a slower lane. Magnets catch steel fragments early, while eddy current separators can kick out non-ferrous aluminum from shredded streams later. Now the line commits to one of two main pathways: mechanical fiber recycling or chemical fiber-to-fiber recycling. Mechanical recycling is faster and cheaper, but it shortens fibers, which limits how new the new garment can feel. Chemical recycling can create near-virgin polymer, but it requires purer streams and higher capital cost. In mechanical recycling, the goal is to turn fabric back into spinnable fiber while preserving length as much as possible. Garments first go through industrial cutters that reduce them into strips to stabilize feed into shredders. Then they enter tearing machines, often called openers or garnet lines, where pinned rollers rotate at controlled speed differentials to pull fabric apart along the yarn path. This is not brute force. Roller speed, pin density, and feed rate are tuned to minimize fiber break while still liberating knots, seams, and inner linings. Dust control is a core engineering requirement here, because shredded cotton creates fine lint, and fine lint is both an air quality hazard and a fire hazard. Extraction ducts maintain negative pressure, cyclones remove larger lint, and baghouse filters capture fines. Many facilities install spark detection and automatic extinguishing in ductwork, because a single hot bearing on a shredder can turn airborne lint into an ignition event. As fibers open up, the line cleans them. Vibratory screens remove buttons and hard fragments. Air classifiers separate light lint from heavier trash, and optical sorters can eject colored plastic pieces that would later show up as specks in yarn. The cleaner the fiber at this stage, the less yarn breakage and fabric defects downstream, which directly controls how much recycled content a premium brand can put into a garment without disappointing customers. The biggest limitation of mechanically recycled cotton is fiber length. Every opening step shortens staple length. So plants blend recycled fiber with virgin cotton or with longer recycled sources to restore spinability. Blending is done by weight using automated feeders because a few percent swing changes yarn strength and pilling behavior. The blend then goes through carding, where rotating cylinders align fibers into a web and form sliver. Carding also removes remaining trash and neps, and modern cards run with sensor feedback for flat settings, suction pressure, and waste rate to keep the sliver uniform. Spinning depends on the target product. Open-end rotor spinning tolerates shorter fibers and is common for recycled cotton. It's producing sturdy yarn for fleece and denim-like fabrics. Ring spinning gives higher strength and smoother yarn, but demands better fiber quality. So it's used when recycled content is lower, or when blending includes longer fibers. Airjet spinning can also be used for certain blends, trading softness for speed and lower hairiness. In all cases, the line monitors yarn evenness with capacitive sensors, flags thick and thin places, and automatically clears faults so a single bad sliver doesn't ruin kilometers of yarn. Mechanical recycling of polyester follows similar opening and cleaning steps. But polyester fibers behave differently under tearing because they are stronger and more elastic. That elasticity is a double-edged advantage. It survives opening better than cotton, but it also tends to entangle, so the line uses different roller geometries and anti-wrap features. For high-quality recycled polyester yarn, many plants avoid pure mechanical respinning from old garments and instead convert polyester back into pellets through chemical routes, because pellets can be melt-spun into consistent filament. Chemical recycling is where the machinery starts looking like a chemical plant, because the objective is to return polymers to a controllable near-virgin state. For polyester, the factory may use depolymerization methods such as glycolysis, methanolysis, or hydrolysis. In glycolysis, shredded polyester is reacted with ethylene glycol under heat and catalysts to break PET into oligomers, which are purified and repolymerized. In methanolysis, methanol breaks PET into monomers like dimethyl terephthalate and ethylene glycol, which can be distilled for high purity. The point of these routes is that dyes, finishes, and many contaminants separate during purification, so the output can meet fiber-grade specifications. For cotton and other cellulosic fibers, chemical recycling often resembles regenerated cellulose production. The plant dissolves cellulose in a controlled solvent system after removing non-cellulosic contaminants, then filters and reprecipitates it into new filament, similar in concept to lyocell processes. Dissolution requires tight control because cellulose doesn't melt. It must be solvated without excessive chain degradation. Viscosity measurements act as a proxy for polymer chain length, and chain length controls fiber strength and pilling resistance. In the final fabric, blended fabrics are the hardest category, and the reason textile recycling is considered high-tech. A common blend cotton with polyester and a few percent elastanic cannot be cleanly recycled by a single method unless the plant can separate components. Some systems dissolve cellulose while leaving polyester intact, then filter out polyester and recycle it separately. Others depolymerize polyester while keeping cellulose in a solid fraction. Separation is driven by solvent selection, temperature, and filtration strategy, and the economics hinge on recovery rates and solvent reuse. Solvent recovery is a major piece of the engineering. Dissolving cellulose or separating polymers is not viable if solvents are lost or contaminated. Plants use multi-stage distillation, membrane filtration, and activated carbon polishing to keep solvent loops closed. Heat integration recovers energy from hot streams to preheat cold feeds, because evaporation and distillation are energy intensive and can dominate operating cost. Once the plant is purified, polymeretha, cellulose dope for regeneration, or polyester. Pellets for melt spinning. The process returns to textile manufacturing physics. Polyester pellets are dried to extremely low moisture because water causes hydrolytic chain adhesion in the extruder, reducing yarn strength. Desiccant dryers hold dew point targets, and inline moisture sensors verify pellets before they enter the spinning line. Melt spinning turns pellets into filament through extruders, screen packs, and spinnerets with hundreds of capillaries. Gear pumps stabilize flow so every filament has the same denier, because denier variation causes weak yarn and visible fabric streaks. Quench air cools the filaments uniformly, and the filaments are drawn to align polymer chains, increasing tenacity. Texturing jets add crimp and bulk to mimic cotton-like hand feel, which is critical when a brand wants recycled polyester to feel premium rather than plasticky.
The quality of this cotton is exceptional.
It really is. I really is. I love the cut on this navy one right here.
I love the color on this one.
It really pairs well with the denim. The tailoring on that blazer is exquisite. It really is. It really is. Ralph Lauren always delivers. The texture of this polo is exceptional.
And this red dress shirt is simply stunning. I think we have our outfits.
Regenerated cellulose spinning uses a wet or dry jet wet spinning approach depending on the solvent system. The cellulose solution is extruded through spinnerets into a coagulation bath that precipitates solid fiber. Bath composition, temperature, and line speed determine skin core structure, luster, and strength. The newly formed fibers are washed repeatedly to remove residual solvent, then dried under tension to prevent shrinkage and maintain consistent linear density.
Thank you for shopping
Quality.
with us.
Control runs continuously because recycled feedstocks amplify variability. Yarn is tested for tenacity, elongation, and hairiness. Fabric is tested for pilling, dimensional stability, and color consistency. Chemical recycling streams are checked for residual catalysts, monomer purity, and intrinsic viscosity, because slight deviations show up as dyeing defects or premature wear in finished garments to make new clothes. The factory then integrates recycled yarn into knitting and weaving. Knitting machines can run at extremely high speeds, but they are sensitive to yarn friction and weak spots. So recycled yarn specs are tuned to reduce breakage. Weaving demands even tighter control because warp ends run under constant tension. Uneven yarn creates striping and loom stops. Finishing lines, scouring, dyeing, and heat setting are calibrated for recycled fibers because residual oligomers in polyester can cause dye spots if purification wasn't sufficient. And regenerated cellulose may shrink differently than cotton. The environmental gains only materialize when the entire system is measured. That's why brand-linked recycling programs rely on mass balance, accounting, and chain of custody certification. Tying recycled output back to quantified input streams, Digital traceability may include QR-based batch IDs, audited claims for recycled content, and restricted substance compliance so recycled garments meet the same safety standards as virgin ones. The real engineering achievement is that these machines don't just process waste. They create predictable material from chaos. They classify polymers at conveyor speed with spectroscopy, separate trims and contaminants with multi-stage mechanical systems, rebuild fiber with controlled spinning physics, and close chemical loops with solvent recovery and purification, turning used apparel into new. Wearable fabric at global scale is less like recycling paper and more like running a combined sorting plant, polymer refinery, and textile mill built to turn mixed wardrobe waste into consistent yarn that can be cut, sewn, and worn every day.